Hello and welcome to our class for today. Today we are going to be looking at a shear force and bending moment question. In this question, we are asked to draw the shear force and the bending moment diagram. So this problem is under a case of a simply supported beam that has a consecrated load not at the midspan, So this is what we have. So we are going to be drawing the shear force and bending moment diagram. Of course, before that, we are going to be doing some calculations. So let's proceed. So the first calculation we are going to be doing is we are going to be considering the upward force and the downward force. All the forces on this beam, we are going to be considering them. So we know that the sum of upward force is equal to sum of downward force. And for this beam AB, we know that we have a support here, so there will be a reaction RB at this point. We also have a support here, so there will be a reaction RA at this point. So sum of upward force, like I said before, will be equal to sum of downward force. So RA plus RB will be equal to 2 plus 4. So our RA plus RB will be equal to 2 plus 4. So RA plus RB will be equals to 8 kilonewton. This will be our This is 6 kilonewton. Sorry for that. This is equation 1. Now next, we are going to be taking moment about point A. Summation of moment about point A will be equals to 0. Now summation of moment about point A will be nothing but RB multiplied by the perpendicular distance, which is 8, minus Now for this, we are going to be considering all upward forces as positive. We are considering upward force to be positive and downward force to be negative. So we are going to proceed. So like I said, RB, that which is our force at this point, multiplied by its perpendicular distance, minus 2 kilonewton multiplied by its perpendicular distance, which is 7 meter, minus 4 multiplied by its distance, which is 6 meter. I hope you get that. So this will be nothing but RB multiplied by 8 minus minus 2 multiplied by 7 minus 4 multiplied by 6, everything equal to equal to 0. RB multiplied by 8 is nothing but 8 RB, minus 2 times 7 is 14, 6 times 4 is 12, that is 24. So we have 24 equal to equal to 0. Minus 14 minus 24 is nothing but 38. So we have 8 RB minus 38 to be equals to 0. So if I take 38 to the other side, I have 8 RB to be equals to 38. So if I divide both sides by 8, 8 will go with 8. My RB will equals to 4.75 kilonewton. I hope you get that. So next, I'll be calculating I'll be looking for my RA. So we can say from equation 1, from equation 1, we have RA plus RB to be equals to 6 kilonewton. If I substitute 4.75 here, this implies that RA plus 4.75 will be equals to 6. If I take 4.75 to the other side, RA will be equals to 6 minus 4.75. This implies that this will be equals to 1.25, of course, kilonewton. So I have my RB to be RB 4.75 kilonewton. So this is what I have as my RB. And then my RA will be nothing but It will be nothing but 1.25 kilonewton. Now let's proceed. Now we are going to be looking for our shear force. We are going to be doing our shear force calculation. So let's start. So we have shear force calculation. Now we are going to be looking at for our shear force calculation. Now, before we do that, for our shear force, we are going to be taking all upward forces to be positive and downward forces to be negative. So if you consider our shear force, if you take our shear force at this point, it will be nothing but RB. Our shear force at point B will be nothing but the reaction at point B. So S dot F subscript B will be equal to what? 4.75 kilonewton. So next, we are going to be taking our shear force at point, so we can call this point C, and we can call this point D. So let's take our shear force at point D. It will be nothing but what? This point, which is 4.75 minus 2. So our shear force at point what? At point D, at point C rather, will be equal to what? 4.75 minus what? Minus 2. 4.75 minus 2 is nothing but what? 2.75. So this is equals to what? 2.75 kilonewton. So next is our shear force at point D. So our shear force at point D will be nothing but what? 4.75 minus 2 minus 4. I hope you get that. So our shear force at point D will be equal to 4.75 minus 2 minus 4. So so if you calculate this is nothing but what? Minus 1.25. So we have minus 1.25 kilonewton. Good. Now for A, we have what? We are going to be calculating our shear force at A, and it will be nothing but what? 4.75 minus 2 minus 4 plus 1.25. So let's do that. So we have our shear force at A to be equal to 4.75 minus 2 minus 4 plus 1.25. So minus 2 minus 4 is minus 6, we have 4.25 multiplied by what? 1.25. This will be 6. This will be 6. 6 minus 6 is nothing but 0. So our shear force at A is equal to what? 0 kilonewton. So this is what we have. So next, we are going to be looking for our bending moment. Let's do our bending moment calculation. So our bending moment calculation now. So our bending moment calculation. So of course, this is a simply supported beam. As always, our bending moment at reaction B and reaction A will be what? Will be 0. So next, we are going to be looking for the bending moment at point C, since our bending moment at B is 0. So bending moment at C will be nothing but what? The force that is the perpendicular distance. So if you take your bending moment at point C, it will be nothing but what? 4.75 multiplied by what? The distance, which is what? 1 meter. So our bending moment, first our bending moment at B, we say is equal to 0. So our bending moment at point C will be equal to what? Will be equal to 4.75 multiplied by what? The perpendicular distance, which is 1. Everything is equal to what? 4.75 kilonewton meter. Now for bending moment, we are still using we are still considering our upward force to be positive and our downward force to be negative. All right. So next, we are going to be looking for the bending moment at point D. So the bending moment at point D will be nothing but what? 4.75 minus what? Minus 2. No, the bending moment will be 4.75 multiplied by 2 rather, minus what? 2 multiplied by 1. Don't forget, this is not shear force. This is bending moment. It's what? Force times perpendicular distance. So 4.75 multiplied by 2 minus 2 multiplied by 1. So our bending moment at point C will be nothing but what? At point D rather. At point D will be nothing but 4.75 multiplied by what? Multiplied by 2 minus what? Minus 2 multiplied by 1. Now 2 times 1 is what? Is 2. 2 times 4.75 will give us what? So let's write this down. So this is 9.7 minus 2. This is our bending moment at D. So 9.7 minus 2 is what? No, 9.7 minus 2 will be 7.7. So this will be 7.7. 7.7 kilo Newton meter. And of course, bending moment at A is nothing but 0. So this is what we have. So from all this that we have just done, we can draw our bending moment diagram and our shear force diagram. So let's do that quickly. So first thing first, as always, we are going to be drawing our dotted line down from each point where there is the load or force. So from here, we have a dotted line here, here, here. So from this point, we have our dotted line here. This will be our reference line for our shear force. Let's take this as our reference. This. So where here is 0, here also is 0. So for our bending moment, we are going to be using this as our reference line. Here will be what? Our reference line. So this is what we have. So here is 0, here also is 0. Now, what is our shear force at point B? Our shear force at B is nothing but 4.75. So we are going to trace this point up. Let's use here as 4.75. So we can take here to be 4.75 kilonewton. So this is what we have. This is 5. So we are going to be, of course, representing this free space with a constant line, since we have no force between B and C. So let's go to this point. Now at C, our shear force is nothing but 2.75. So we are coming down to this point. Let's take this point to be 2.75. So we have 2.75 kilonewton. Now, of course, similarly, let's move to this point. Now at point D, we have our shear force to be nothing but minus 1.25. So we are going to be going towards the negative side, even as we get our minus. So let's take this as our minus 1.25. This is minus 1.25 kilonewton. So, and then as always, since there is no load in between, we represent that with a constant line towards the side. And our shear force at A is equal to 0. So we go back to 0. So this is our diagram for our shear force, where this area is positive and this portion is negative. So that's that for our shear force diagram. So up next is our what? Is our bending moment diagram. Now for our bending moment diagram, we know that bending moment at point at B is 0, bending moment at A2 is 0. So our bending moment at C is 4.75. So we are going to be tracing 4.75 upward, even up to C. So from this point B, we are going to be going 4.75. So we can just take this point to be our 4.75. So, and don't forget that for every straight line on the shear force diagram, it's going to be represented with an inclined line on the bending moment diagram. So this will be what? 4.75 kilonewton meter. So this is 4.75 kilonewton meter bending moment. Now for our bending moment at point D, we have bending moment to be what? To be 7.7. So we are going to be going upward again. Let's take this point to be 7.7. So this is 7.7 kilonewton meter. So this is what we have. So next we are going to be what? We are going to be taking this line downward because our bending moment at A is nothing but 0. So we are going back to 0. So this is what we have from this point even up to this point. So that's it. So this, of course, we only made use of the positive direction. So this is what we have. So this is our bending moment diagram. And this is our shear force diagram. So thank you for watching. I hope you understand and comprehend all we have just done. So of course, stay tuned for more and more numericals on shear force and bending moment. Thanks for watching.